If you can't trace retrieval, you're debugging RAG blindfolded. Add traces that explain every chunk choice. This is the workflow you'll know how to run when we're done, which traces retrieval and explains why the chosen chunk answers the question. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Retrieval Observability answers a simple emergency question. Why did the system pick that document and not another? Engineers reach for it when answers drift, when users get wrong or irrelevant results, or when latency spikes. Success looks like a trace you can read end to end with reasons attached, not just a final answer. At a high level, tracing retrieval means emitting events for candidate scoring, filtering, re-ranking, and final assembly. Think of it as a timeline that shows each decision and its numeric justification. That timeline turns a mystery bug into a short investigation. We will build a tiny tutorial trace for a retrieval augmented generation flow. You'll send spans and events to a local Jaeger, score 3 example chunks, filter them, re-rank the survivors, and assemble a response while recording why each step acted. No heavy infra required, just a clear path you can replicate and extend. Now we'll wire OpenTelemetry to a local Jaeger so traces have a home. This snippet configures OpenTelemetry to export traces to a local Jaeger. It begins by importing the OpenTelemetry Trace API and the SDK's trace module, plus Jaeger exporter. The code creates a tracer provider and sets it as the global provider, so future spans use this configuration. A batch span processor is attached with Jaeger exporter pointing to localhost via the agent port, which batches spans efficiently before sending. Finally, getTracer returns a tracer named RAG tutorial for this tutorial spans. The printed tracer name confirms OpenTelemetry is initialized and wired to Jaeger, so subsequent spans will be visible in the UI. Next, we'll emit scoring events, so each candidate gets a visible score in the trace. This example emits candidate scoring events on an OpenTelemetry span for clear retrieval observability. The variable query holds the user text, while docs is a tiny ID to text store to keep this focused. Inside tracer.startAsCurrentSpan, named retrieve.candidates, the code builds a query token set and loops through docs. For each candidate, it computes a simple overlap score normalized by document length. Then call span.addEvent with candidates scored and attributes for ID and score. All candidates and scores are collected and sorted, so the top item is clear. The printed top ID and top score show which chunk currently wins and at what score. Now we'll record the filtering step, so you can see which candidates were dropped and why. This code records filtering decisions as OpenTelemetry events, so you can see exactly why items survive or get dropped. A threshold min score defines the cutoff for relevance. Within a new span named filter.candidates, the loop examines each candidate's score pair from earlier and decides an action of kept or filtered out. It logs a filter event with attributes for ID, score, and action, giving you explainability in Jaeger during incident-style debugging. Matching candidates are appended to kept for downstream steps. If you raise min score, fewer items will pass and latency may drop. Lowering it retains more candidates at the cost of extra re-ranking work. The print confirms how many items were kept at the chosen threshold. Next, we'll re-rank the survivors and attach explanation metadata for auditability. This snippet re-ranks kept results and records explanation metadata as OpenTelemetry events for downstream auditing in Jaeger. It starts a re-rank span and defines reasons, where a Solar intent boost simulates a query intent signal. The loop considers up to top K items from kept, computes a re-ranked score RS, and adds a re-rank.item event with ID, base score, final score, and reason. It collects all entries, sorts by the new score, and picks the best item for the answer chain. Increasing top K can improve accuracy, but adds cost. Decreasing it saves latency. The print shows which candidate won after re-ranking and the reason that influenced it. Finally, we'll stitch a root trace that records timing and the chosen response for clear root cause analysis. This example creates a nested OpenTelemetry trace that stitches the full RAG path for quick root cause analysis in Jaeger. The root span rag.query stores the original query as an attribute for easy faceting. A child span embed marks a cache hit to highlight latency savings. Another child span vector .search sets a synthetic latency.ms attribute using the document count to illustrate timing in the trace. The final child span response assemble emits a chosen event showing the selected candidate and its final score. This compact structure lets you answer why this chunk and how long each stage took. The printed output confirms the chosen ID and that events were recorded. This little toy maps directly to real systems. Replace the simple overlap score with your embedder and ANN search. Replace intent boosts with model signals. The trace shape stays the same and gives you the same explainability. Recap. It is tracing retrieval decisions with events for scoring, filtering, re-ranking, and assembly. Use it when answers need auditing or when debugging relevance regressions. Caveat. Adding events costs CPU and storage, so add the right level of detail for your production budget. Next step. Increase the re-rank top K and measure accuracy and latency so you can pick the best trade-off for your workload. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.